you for coming, everyone in person and online. I hope you enjoy this event that we've put together for you. I am extremely excited to be able to chair this event and have some amazing speakers. But first, I'd like to give an introduction to the topic and why it's important and why we are addressing it here. So materials are very important as we are transitioning into low-carbon systems, because we need to have more and more specialized materials for the systems that we are building. There's many kinds of materials. There's steel, there's cement, copper, lithium, and they go into different types of infrastructure and technologies. So to give you some examples, materials such as steel, cement, or chemicals are known as the hard to decarbonize sector because they are the ones that require a lot of energy for production or because they emit a lot of CO2, owing to factors such as coal use in steel making, for example. There's also implications of lifetime of these materials and how when producing plants for them, it takes a long time then to phase them out. There's also materials that we are now knowing as critical, or that we're calling critical, and they include things like lithium, cobalt, copper, or rare earths, and these materials are essential for technologies used in digitalization or in renewable energy, and electric vehicle batteries, of course. These types of materials, for example, rare earths, are used in very small amounts, and they're really necessary for the application. So, for example, neodymium is used in wind turbine magnets, and it's a small amount, but it really makes the magnet really strong. There's also other worries, like human rights aspects related to mining, or the increased demand of certain technologies versus the mining project lifetimes. And it's estimated that it takes 16.5 years to go from a mining project from discovery to production. There's also some geographical concentration of some minerals that is presenting problems for security. So all of these aspects really come together, and it makes us really wonder what can we do about the material implications as we build these systems. Since we need to tackle many of these aspects, I have a great group of speakers with me today who might help us discover what material efficiency strategies might be available. And actually, it's been estimated that 30% of combined emissions reductions could come from materials, from certain hard to decarbonize materials. So it's really, really important that we do this. So without further ado, I'd like to introduce Peter Levi, who is our industry lead at the International Energy Agency, who I'm very happy to have here with us. Peter, the floor is yours.
Thanks, Karla. Sorry. Thank you very much, Karla, for the lovely introduction. And just to say thank you to the organisers, to CCG, and also to my fellow panelists, and great to see John on the line as well. It's actually not been too long since I last saw John, which I'm happy to say. So I'm going to start to talk about bulk materials, and I believe my fellow panelists will be addressing the critical minerals part of the equation. So I'm going to focus on the bulk materials and the scenario modelling that the IEA does for this aspect of the energy transition in our net zero emissions by 2050 scenario. And I think I have some slides that might be coming up shortly. Thank you very much. So just a very brief introduction to some of the work that the IEA has been doing on these industrial sectors or subsectors of industry, and also the industry sector as a whole, and how that fits into the broader flagship publications of the IEA and the energy system modelling we do. So we started a series of roadmaps way back in 2009. These are technology roadmaps. So the first one was actually on the cement sector, but these are 30 or 40, I think close to 40 technology roadmaps that cover different technologies and sectors of the energy system and the key steps, milestones that need to be taken to be reached, rather, in each of these areas. We've followed this up with a new series of roadmaps, or a slightly revamped series of roadmaps, I would say. These are longer publications with a slightly more kind of pedagogical element to them. The iron and steel technology roadmap was the first installation of that revamped series, and the ammonia technology roadmap is the latest one there. We also have other deep dive series under other titles, and we have recently conducted an analysis of critical minerals, the role of critical minerals in clean energy transitions, and this is a, well, not so new anymore, but evolving work stream of the IEA and our core kind of areas of energy security and also sustainability and providing those. I'm going to stay away from that topic today, but I will just highlight our publication there. These deep dives and technology sector roadmaps fit into our kind of flagship publications, the World Energy Outlook and the Energy Technology Perspective series. And what I'm going to talk to you about today was the special report we did on net zero emissions by 2050. I should just also highlight that we are increasingly doing country roadmaps, so exploring that other dimension, that geographical dimension of transitions in each of these areas. So for the eagle-eyed among you, you'll notice that these are numbers from the 2021 edition, or the first edition of the net zero emissions by 2050 scenario. The World Energy Outlook 2022 edition has just produced an update of this scenario in full. This has come out since I prepared these slides, but you will be able to find updated numbers on this scenario in that publication. No, not huge changes, but we have updated the scenario to take account of recent events, notably the Russia's invasion of Ukraine. The point of this slide, to provide the overall picture of the energy transition, is to say that different sectors move at different speeds. And this is for a number of reasons, but chief among them, I would say, is to do with the readiness of technologies, the availability of technologies that we have commercially available in the marketplace today in each of these sectors. We can see very rapid progress in the power sector on technologies like solar PV and wind. We can see in the transport sector, in light-duty vehicles and passenger transport, we can see rapid increases in sales in electric vehicles for passenger travel. But this progress that we're seeing is not universal to all sectors. And so in the industry sector, we would count this sector among those, as Karla noted in the opening, that, well, subsectors of industry, steel, cement, and chemicals, as those which we would call those with hard-to-abate emissions. And it's because of this statistic here, this result from the modelling of the decomposition analysis that we do, that shows that industry is an area where we see several of these technologies that, again, we don't have commercially available today, and the bringing those through to kind of a large-scale commercial deployment is something that has a certain lag to it. We are tracking all of these developments in all of these areas in our various publications, the Clean Technology Guide and Tracking Clean Energy Progress. These are annual updates looking at each of these areas. But the key thing to note there is that while we're seeing progress, there are still significant innovation milestones that need to be reached in some of these areas. Focusing on industry, so we have these three hard-to-abate heavy industry sectors I noted. So we've got the chemicals, steel, and cement sectors, and we can see here on this slide the emissions trajectories from those sectors in the net zero emissions by 2050 scenario, broken down by between advanced and emerging market and developing economies. And we can see that around 4/5 of emissions from producing these three materials, and also the rest of industrial activity that we categorize within the industry sector, takes place in those emerging market and developing economies today. And that will be a particularly important consideration in terms of where support and where the kind of real technology deployment challenges are, that I'll come to at the end of the presentation on a note on policy. The other key message of this slide is that there are very few residual emissions left in industry. We talk in direct emissions in the IEA generally, because we are modelling the whole energy sector. So this is around 9 gigatons of emissions in 2020 for global industrial emissions, and this is falling to residual emissions of around 400, 500 megatons. So this is a very small percentage that are left on a direct emissions basis. Just to go into a bit more detail on why these sectors are hard to abate or challenging, Karla mentioned some of the key reasons there at the beginning. So the use of fossil fuels to provide energy services that are difficult to electrify with the technologies that we have on the market today. This is a very important point, and fossil fuels unfortunately provide these services, these energy services of high temperature heat, reductants for iron for producing crude steel, and also as feedstock in the chemical sector. Fossil fuels are a convenient and cost and cheap source of those energy inputs today, relative to the alternatives. Of course, we see energy markets in turmoil at the moment with the global energy shock, but still, relative to the other options we have available, a convenient source of those energy services. Another key technical part of the challenge, and I'm just showing the steel sector here, the iron and steel sector, is the large capital-intensive and long-lived stock of existing assets in the sectors. So relative to a typical lifetime of around 40 years on average globally for iron-making equipment, we're showing blast furnaces and DRI furnaces here, the global stock. We see that the average age globally is around 15 years old for iron-making equipment. And these are the most emissions-intensive assets, so they're only around a third of the way through their lifetime. China's gigantic coal blast furnace stock there is shown. This is accounting for around, more than half of global iron-making capacity. This is an important challenge for the country there, but this should not be, looked at in quite the same light as the rest of the world's stock, in the sense that China's the availability of scrap for producing via secondary steel production through electric furnaces is likely to increase a lot in the coming decades. So these blast furnaces were built very rapidly, and so they're very young, but they will also be subject to a huge wave of scrap that becomes available in the future. If we left these assets as they are and we operated them towards to the end of their technical lifetimes, to the end of the lifetimes at which they're typically operated today, and we didn't change the operating conditions, we would use up more than the cumulative emissions budget that's allocated to the industry sector in the net zero emissions by 2050 scenario. The key opportunity, though, is that there is a 25-year investment cycle associated with lots of these heavy industry assets. So this is not just steel, this is also chemicals, steam crackers, cement kilns, and other kind of capital and energy-intensive equipment in these sectors. If we intervene at the end of the next investment cycle, we can save around 40% of the cumulative emissions that would otherwise be emitted. Existing assets are only part of the problem, though. We need to look at what the new assets that would need to be built in these sectors, and I'm going to move it along because I don't want to use up more than my time, but this decomposition analysis shows from 2020, so there's a temporal decomposition from 2020 to 2050 in this net zero emissions by 2050 scenario, the mitigation measures and the maturity of those measures with respect to the emissions reductions over that time frame. So just on the mitigation measures, we see that in these heavy industry sectors, so this is just steel, cement, and chemicals shown on this slide, we see the contribution from carbon capture and from electrolytic hydrogen to technology families that would be also contributing. These would generally be among these technologies that I mentioned that are generally not at commercially availably, they're not being deployed at commercial scale today. In many industrial application instances, even if we are seeing increasing sizes of electrolyzer projects around the world and actually renewed momentum in the carbon capture space, we're still seeing a significant lag in specific applications in industry that are very important. So CCUS, very important in the cement sector for capturing process emissions, although alternative raw material inputs to limestone may offer a pathway to reduce the need for CCUS in the cement sector in the future. At the moment, we are seeing demonstration projects for carbon capture somewhat lagging behind the deployment levels that are needed in the net zero emissions by 2050 scenario. Electrolytic hydrogen, important in all three heavy industry sectors, less so in cement, but still providing some of the high temperature heating needs. And in the chemical sector, playing a massive role for feedstock, particularly for high-value chemicals, particularly for ammonia, methanol, and to some extent for high-value chemicals. The other mitigation measures on the left-hand bar are those that I'm sure are very familiar to you. Karla mentioned material efficiency. I'd like to place a particularly important emphasis on this category of strategies. Here we're talking about recycling, of course, but also extending the life of steel and cement and chemical using products. So extending their lifetime and therefore delaying the point at which they need to be replaced, and therefore the amount of material that needs to constantly flow into these end-use sectors. Lightweighting, modular design practices, direct reuse of products without remelting them. These are all strategies that can contribute to, we see around a potential of around a fifth or a quarter reduction in the total amount of demand for these materials that's needed in 2050. And that is all embedded, that analysis is all embedded in the net zero emissions by 2050 scenario. And then just to reiterate the point on the right-hand bar, this is really about the readiness of these technologies. So for the heavy industry sectors, we see that more than half of the emissions reductions through to 2050 are achieved using technologies that are at prototype or demonstration phase today. So we're really doing a decomposition analysis at the individual technology level and looking at the contribution of, say, hydrogen-based direct reduction or electrolytic hydrogen for ammonia feedstock, and looking at the contribution of each of those technologies, and these are the results there. On these measures that I put under the kind of CCUS and hydrogen, but also some direct electrification technologies, let's call them near zero technologies, although we're in some other work, we're refining the exact definition of that term, but technologies that can really deliver substantial emissions intensity reductions for primary steel making, for cement and clinker production, and for primary chemical production. We see that the role of those technologies by 2050 is really huge, and they are providing little to no contribution to the sector today, again, because of this technology readiness component. So we're looking at upwards of 90% of production of these three materials by 2050 is via these near zero emissions routes, so routes that can produce clinker, primary steel and primary chemicals with this kind of 90% plus emissions intensity reduction in many instances. Most of what I've spoken to you about so far is about technology and mitigation strategies on the kind of in the technosphere, as I would refer to it. That's the other side of the industrial decarbonization coin, is policy, of course. I don't have too much time to unpack this framework, but we've done quite a lot more work on this recently this year in a report for the German G7 presidency, which our executive director actually presented aspects of, or in his remarks, at the Climate, Energy and Environment Ministerial of the G7 ministers back in May, and he also participated in an event this week with Chancellor Scholz on the climate club concept, of which our industrial decarbonisation work for the G7 will hopefully form a component of the inputs to that consideration. On this policy slide, three or four things to highlight. Collaboration will be incredibly important. There are multiple dimensions from a collaboration, whether it be investment, infrastructure, standards and definitions, innovation, R&D. These will all be important dimensions for collaboration between the private sector, between the public sector, and between non-governmental organizations and research institutes and so on. We need to have a long-term signal that's provided to producers so that they can plan their investments in an effective manner. As I mentioned, lots of these assets are very long-lived, so we need to give a signal to people who are investing money in these sectors of what's required in the future. And then we'll need a series of targeted actions in specific areas, existing assets, as I highlighted at the beginning, particularly in emerging market and developing economies, where there are still several emissions-intensive assets being built today, and in all likelihood will be built over the next few years. We need a specific series of strategies on the financing side and also on the technology side to address them. And then lastly, just to highlight the enabling conditions. So tracking data, of course, is very important. Planning and developing an infrastructure, and also this level playing field element, which we're hearing talked about a lot in the context of trade in these materials, which I should have mentioned is another aspect that makes them hard to abate in many instances. I'm sorry if I've run slightly over time. I can't see a clock, but I'm going to pass over to the next speaker, or pass back to Karla, rather.
Thank you so much, Peter. That was incredibly interesting, and you gave us a lot to think about in terms of what needs to happen, and rather quickly, if we're ever to achieve this emission reductions. Yes, thank you. A round of applause. Our next speaker is Jonathan Cullen, who's joining us online. He is a professor of sustainable engineering at the University of Cambridge, and actually happens to be my boss. So I'm handing it over to John.
Hello. Sorry, I was just trying to find the unmute button. Thank you very much, Karla, for that introduction, and thank you, Peter. Always great to see the work that the IEA is doing in this space. I wanted to, can you see the slides all right? Is that okay?
Yes.
Great. My name's Jonathan Cullen. I run a group called the Resource Efficiency Collective, which both Karla and Peter have been a part of in a past life for Peter. And we try and seek answers to this challenging question of how do we deliver what the future energy and material services that people want, while at the same time reducing resource use and environmental impact. So when we're thinking about this problem of the material impacts of kind of future low carbon technologies, the starting point for me is looking at how much materials we need for different technologies. And I've just brought up an example here, delivering a megawatt hour of electricity. By coal, we need about 1.1 kg of different materials, but by wind, we need 12.7 kgs of materials. So we see this shift going on where in the 20th century, it was, you know, about access to fossil fuels, coal, oil, gas, etc. And these were essentially flows of energy. And in the 21st century, we're moving in as we decarbonize, as we go towards renewables, we're moving into technologies that require a lot more materials for the same output of electricity. And the challenging thing for us as kind of modeling is these are stocks of materials. These materials last for many years. Energy, we can account for just on year, just the flow. Energy flows is what we've been doing, and we're very good at accounting for energy flows on a year-by-year value. But now we're moving into a space where we need stocks. Also, in those materials that go into these technologies, there's a lot more materials and different materials, a lot more complexity in the products that we're having to design and deliver. So we wanted to try and look at that gap in the literature, which was how much embodied emissions, how much investment of CO2 do you need to make these new technologies, particularly electricity generation technologies and technologies for for transport. How much investment of CO2 do you need to make to get back out these low carbon technologies, so renewables, for example? And we've created this piece of software called MATDP, Material Demand Projections. Karla's been involved with that with myself in making that as a part of a project called Climate Compatible Growth, which is sponsoring this or hosting this event. So what does MATDP do? It looks at these material implications of changing our energy and transport systems, and it can help countries prepare pathways or be prepared in terms of industrial capacity. How many steel plants or cement plants or solar panel manufacturing facilities do they need in that country if they were to build them in their country to supply this generation? And we've been applying this model in different cases. So today I'm going to talk about 47 African countries that we've done some work on, but we've also been applying this in Indonesia and Laos, and 69 other countries as part of an energy starter kit. And we're starting to do transport as well. And at the base of the model is these kind of 16 electricity technologies or electricity generation technologies. So everything from, wind, different size wind, solar, hydro, nuclear, coal, gas with CCS and without. So we've got those technologies in there, 43 different transport technologies that we're looking at. And then we map them onto 53 different materials. And these are a mix of the bulk materials, which Peter was talking about, and also the critical materials, which we're going to hear about later in this session. And importantly, we're making this all available online. So that's the kind of the Python model that we've built to do this, the kind of online live generator, and the model results are all available online, but also all the data that feeds into this. So if people want to get engaged and play with scenarios about future generation technologies, they can, and they'll be able to see what the material implications are of those different choices. So just to introduce what we did with these countries, we applied MATDP to 47 African countries. We used 3 scenarios, so a reference scenario that takes into account the national energy policies in place at 2017, and then a 1.5 degree and a 2 degree scenario, which aligning with the Paris agreements. And as a start to the model, we take in exogenously or from outside the model, we take in electricity generation forecasts. And in another part of climate compatible growth, we're producing these forecasts in different models and allowing countries to produce their own forecasts. So here we just have some examples. This is at the top, we've got power generation capacity required from now through to 2070, and and the actual power generation in the bottom half of those graphs under our 3 scenarios. And you can see that we're projecting a 10-fold increase in electricity generation capacity from now through to 2065 to meet growing electricity demand in Africa. These graphs are for these 47 countries. And there's slight differences, but not huge, in the differences between the reference scenario, the 1.5 and the 2 degree scenario, which is interesting. It means that, I guess, what we would build going forward in the future and what's cheap is actually becoming the low carbon technologies that we're talking about. Just to zoom in on that and just to see a little bit more, this is the 2 degree scenario for power generation. You'll see there's wind in there up top in darker pink. There's a big chunk of solar PV coming through. There's some nuclear coming through there in this scenario. And then we still have the more traditional technologies there, but most of the non-CCS is being phased out to some degree. From that input to the model, we can then produce these graphs. This is a graph of how much material we would need in those three scenarios. So the mass of material goes 20-fold over that period. We need mostly concrete there at the top, but also lots of sand, which goes into the silicon for solar panels, and then steel and other materials there, shown by their mass. And then we can convert that into the embodied emissions of those. And so you'll see here some results around the embodied emissions of producing those materials. And we can back out, how much, if these materials were to be produced in Africa, for instance, how many blast furnaces we might need, how many cement plants we might need, how many aluminium smelters we might need. And there's an interesting dynamic that comes out of this about whether countries should be producing these technologies in-house in their own country or just buying them in from overseas. Can also do other things. I'm just showing here, for example, the jobs that might come through from if you local manufacturing jobs and local construction and installation jobs that are associated with putting these technologies in, so we get an idea of what jobs might be created in the country. We can also do things like critical materials as well and back those out. Excuse me. Just as for the conclusions of this study we did on 47 African countries, we need a kind of a joined up strategy that looks at when we're getting direct emissions reductions from increasing the share of renewables, what's the embodied emissions impact of those materials, and making sure we think about that, making sure we decarbonize the industry which makes the electricity generation technologies, the renewables, making sure we decarbonize them first, I guess, before we build all these renewables, so that we're building out with lower carbon and we're not increasing the embodied emissions at the expense of operational emissions. And the shared goals, we need to prioritize industrial decarbonisation to do that. We need to implement material efficiency where we can to reduce as much as possible the materials required. And we need to increase the regional and international cooperation and really look at this thing of where should these technologies be built and where should the jobs and the investment come from for these technologies. Thank you.
Thank you, John. That was a good angle based on what Peter was saying about what's needed in this type of economies, like the countries that you presented. So it was good to see that distinction and study. Our next speaker, I'm very happy to present, is Jennifer Layke, who is the Energy Program Global Director at the World Resources Institute. Jennifer, the floor is yours.
Thank you so much, Karla. Thank you all. It's wonderful to be here and have such a terrific introduction to today's session from my two previous panelists who've covered some of the points I was going to cover. But let me just frame this for a minute. We know already that half of the global climate change emissions and 90% of global biodiversity and water stress impacts and 1/3 of human health impacts are due to resource extraction and processing. The figures there are staggering, and if we are not paying attention to how we think about resource circularity, minerals, mining, and the use of the Earth's bounty, we will miss our goals. But we've talked for years about the decoupling of energy, of progress, of materials, of economic progress, and we haven't found the interventions. The energy efficiency mandate or world has long been advocating that we have a value proposition that is both compelling in economic terms and in terms of business practice. But there is a significant amount of overarching market barriers and inertia to representing the opportunity in terms of the types of actions that we take within our economy. So there are a number of things that I wanted to touch on today. First of all, is the point that we've got a clear need for a change in the way our markets operate and our business signals are operating, that we are going to require a change in procurement and policy, and that we have an obligation to examine more critically the economic development pathways that we are looking at in terms of the distributional value add and the negative impacts associated with extraction, processing, reprocessing, or recycling, and end of life. So in terms of thinking about the circular economy, if we are to take a look at the outset, I mentioned the scale of the problem. And then the next thing we have to look at is the timeline for this problem. And we've just seen a number of the presentations that highlight how quickly we are growing our demand for these materials and minerals. This will require that we consider how we look at risk management and mitigation. In terms of both the extraction and the processing, there are at least 3 things that we could be doing to develop a broader alignment between our social, environmental, and climate goals and our economic development pathways. The first is really going to be in chain of custody, chain of command, and the governance systems that are going to be required for us to take these ideas forward. That is going to entail a different global economic set of standards or approaches. We've done this before. We've done this with other toxic chemicals that have been traded, or with things like HFCs. When I started my career, we were looking at this in terms of how the global supply and transition associated with ozone-depleting chemicals, and import, export, the tagging and the ability to track chemicals and elements in the economy will be critical. We're working on that, and we have opportunities to do that in the as well as in the wood processing areas, where a number of countries, including the United States, have created the opportunity for a chain of command understanding. So if we're going to look at this from the conversation, from the perspective of how we manage for the type of ownership and chain of control, we have this requirement for business and for government to align and collaborate on these business models that will allow us to track where and how the minerals are in the system. The second thing we're going to need is this multiple tiered system of take-back. This is something that, in looking at our experience with lead-acid batteries, a very good precursor question because of the toxicity. And in the United States, there's about 98% of lead-acid batteries that are brought back into the system and either repurposed, recycled, or retired. And that is not the case in many countries. So again, it's not just about the initial mineral, it's about the product. Which gets me to the questions associated with the mechanisms and how we will begin to implement those mechanisms. Business models such as those that we've used with cellular phones, where one leases rather than owns the asset, and with an incentive for a turning back in. Now, I don't know about you, but my iPhone, they often tell me, is valueless when I bring it back in and I upgrade to my next phone. I have to say that is a very real missed opportunity. So if we're serious about thinking about the circular economy, we would have to be assessing a value to the return from the customer into a distribution, a repurposing and distribution model for those resources. The other thing about the procurement is, or the other thing about changing business models is procurement standards. We have used this mechanism and this approach with renewable electricity purchasing in the corporate space. We've used it with some rare earth minerals from war zones, but we have not done this in a systematic way except on price. And if we continue to use price as our main priority in our procurement, whether that's public or private, we simply will not get the type of decarbonization or performance-based metrics, because the attributes of the economy and the value to the economy will not be realized. And I want to say this is incredibly important because of the distributional impacts on where and how primary production and the initial application may be the cheapest application because of our systems today. So let me just highlight the example of diamonds. And we all are familiar with the blood diamond movement coming out of war zones. However, the blood diamond conversation actually didn't go far enough in terms of building out the recognition of human rights abuses beyond war zones. And so you have a bifurcation of a yes-no material instead of having a performance-based metric that would allow you to evaluate your choices as a consumer, whether you're a corporation or you're an individual. So I think the key for us here is, in terms of getting to scale in the time frame we need, is to look at the mechanisms that would incentivize our return of materials, our products, our ability to navigate and understand the chain of command and custody, and the opportunities associated with the mitigation of impact on the ground from the mining for these materials, by both allowing a change in ownership approaches and by getting to these questions associated with the attributes that we measure beyond cost. So with that, I'll say one final thing, and that is land use issues will be coming up as one of the most significant, scarce and conflicted decisions that policymakers and the private sector are going to face. We are thinking about land as a carbon sink. We are thinking about land for materials. We are thinking about land for our expansion of our economies, whether that's productive use or bioenergy. We are going to have to grapple with those choices. And until we actually have the ability to measure and engage with communities and with our national policymakers about the competition for those resources, we simply will not be able to implement a circular economy the way that we need to redesign. Thank you.
Thank you so much. Those were brilliant perspectives to the uptake of technology that's needed, and definitely things that we need to be thinking about. Right. So our last speaker is Francisco Boshell. I'm very happy to have him with us today. He is the lead analyst at the International Renewable Energy Agency, particularly at the Innovation and Technology Center. And he's also a very experienced practitioner, and I'm very happy to have him. So Francisco, up to you.
Thank you very much, and good morning, everyone. I hope you can hear me well. You can also see the slides. So first of all, thank you very much for inviting IRENA to contribute to this event. Second, thank you very much to the previous speakers. Very, very interesting, insightful presentations on the bulk of materials needed, on the modeling aspects, as well as the environmental and sustainability aspect. I hope that my presentation may complement your presentations. As mentioned, my name is Francisco Boshell. I did the work on innovation at IRENA's Innovation and Technology Center based in Bonn, Germany. And today I want to give you an overview of the work that IRENA has been doing in the last 2 years concerning the need and the bottlenecks regarding critical materials for the energy transition. To give a little bit of context, first of all, according to our flagship publication, the World Energy Transitions Outlook, the energy transition towards a 1.5 degree aligned scenario with the Paris Agreement has 3 main components for the decarbonization. First one is the direct use of renewable energy, which accounts for around a quarter of those emission reductions. Another quarter of those emission reductions should come from energy efficiency measures. And interestingly, another 20% should come from replacement of gaseous and liquid fossil fuels in end-use applications with renewable electricity. Another 10 is coming from green hydrogen. So it's also electricity from renewables, but through indirect electrification. And the other around 20% may come from other technologies such as carbon capture and storage. But basically around 3/4 or more than 3/4 of the emission reductions are related to renewable energy technologies and energy efficiency. And this calls for a huge increase and scale up of the different technologies required for the energy sector coming from utilizing renewable energy sources. What you can see on the right side is our projections on the growth needs for 3 specific technologies. We have, of course, for all the different technologies required for the energy transition, but just as an example, wind capacity. Today, we are around 800 gigawatts of onshore wind and around 60 gigawatts of offshore wind. In 2050, we may need 6,000 and 2,000 gigawatts respectively. So it calls for a 10-fold increase in installed capacity of wind turbines. Solar from around 500 gigawatts today to almost 15,000 gigawatts in 2050. So a 30-fold increase. Electric vehicles from around 7 maybe last year, now we are around 12 million electric vehicles on the roads to more than 1.7 billion by 2050. So a 250-fold increase. So, and we can continue with electrolyzers capacity, with geothermal capacity, heat pumps deployment. Everything requires massive increase. Now, we consider that this is actually feasible, and we have seen the growth rates in the recent years, and we consider that this is economically possible, but of course we have to take into account a number of aspects to materialize this. And by the way, this needs for renewable energy technologies is not coming just from IRENA. 2-3 years ago or 5 years ago, IRENA was saying, okay, you have too high numbers for renewable, but even today, the most conservative agencies now even have basically the same numbers that we presented 1 or 2 years ago. So it's not just IRENA. I think now something positive is that we see more and more consensus from all different stakeholders that this is the pathway to go. So one of those aspects that we, of course, need to consider when we think about this mind-blowing, huge growth of deployment of all these technologies is, of course, materials. We already heard about the bulk of commodities, including chemical, cement, and steel. But there are other, as we discussed, materials that will be needed that are, some people call the critical materials. And first of all, why we call them critical materials? And it's not necessarily because there is a scarcity of those materials in the planet, but it's more related to how to ensure the quantities that are needed due to some difficulties, for example, with mining and extracting those materials, the geographical concentration, the difficulty to replace those materials with other substitutes, the quality of the materials in different areas, and the easiness, let's say, to recycle and recover some of these materials or extend their lifetime. So that's why some of those materials are called critical. In general, said that there are around 35 materials that can be considered critical. For the energy sector, out of these 35, around 30 are really needed and crucial for the energy transition. But here we have 4 examples. The first is copper, that of course is needed for all the required electricity, transmission and distribution grids, batteries, electric vehicles, etc., where we see that there will be a need to increase their supply from around 30 million tons per year today to around 70 million tons per year by the mid of this century. So a 2-fold increase. Nickel, which is now becoming more relevant of batteries for electric vehicles as well as stationary applications, from around 3 megatons per year to around 8 megatons per year in 2050. So almost a 3-fold increase. Lithium, of course, batteries, particularly for electromobility, from less than 500,000 tons per year to around 4 million tons per year. So a 10-fold increase. And rare earth, including neodymium, iridium, as mentioned before by the moderator, needed, for example, for permanent magnets used in wind turbines or in electric vehicles to to increase from 0.03 megatons per year to around 0.5. So again, like a 12-fold increase. Yeah? So clearly there will be a huge increase in demand for all these materials coming from the energy transition. And now the previous speakers also mentioned about the issues about geographical concentration. And here I think it's important to distinguish two aspects. What you see on the left side, on the bars on the left side, is where some of these critical materials are mined. And what you see on the right side is where they are refined and processed. Now, starting from the right, where they are mined and processed, you see a lot of dark blue there, right? This is basically China. So it's clear that in the case of copper, nickel, cobalt, rare earth, and lithium, China has excelled in developing the skills, capacity, and industry required to refine and process those materials. Also because locally there is a huge market for those materials and then economies of scale. But if we look at the left side from where they are mined, you see much less dark blue, except from rare earth. But you see more pink, orange, gray, green, etc. And this is basically what we call developing on emerging economies, including Chile, Indonesia, Peru, Myanmar, Philippines. So when we talk about concentration, it's important to distinguish what we are talking about. Are we talking about the mining? Because mining is much more diversified than processing and refining. And there is a huge opportunity to still diversify much more the mining and extraction, and to develop capacity to also diversify the refining and processing. So these are two topics related to supply that are different and require different strategies. We consider that indeed we will need a huge increase in all these materials, and if we don't act today, this may become a very important issue for the energy transition. But we are also positive from the actions that we have seen from countries in the last couple of years, that this will not be a showstopper. But we need to continue to work on these topics that we have been discussing in this session. The first one is that clearly there will be a huge rise in demand for these materials. There will be a risk in terms of supply that require to be addressed, but also that we need plans for this energy transition that take the need for these critical materials from the beginning or from now, basically, and that we need more transparent information and public cooperation. Today, for example, there is no clarity, for example, on the price of some of these materials on the spot in certain markets, the availability of resources, the number of mining that are being developed, etc. So there is still a big opportunity to have more clarity and transparency. And this is important because this is the kind of signals that the industry will need to invest in more capacity to produce, refine, and process these materials. And also it's important that we consider that every of these so-called critical materials is different and require a different strategy. As said, some are more related about mining, some are more related about refining and processing, some others are more about trading, etc. So there is no one solution for all critical materials. Now, what we have also seen in recent years is, of course, the price volatility. And this is very interesting to see. We see the case of lithium, cobalt, and they are all the time going up and down depending on news announcements of new demand, new scenarios, and this is, let's say, one example, of course, of a market that is very dynamic at the moment, but also the need again for this transparency in information and data to have more security on demand scenarios. The issue about vertical integration. So, of course, more and more countries are considering, and companies, including electric vehicle manufacturers, to have integrated from mining, refining, processing, till the final product integrated or very close to the same location in hubs. So this is another strategy to consider. And of course, what was mentioned also by the previous speakers on the importance of environmental and sustainability. But what we see there as an issue is that many companies have these ESG parameters and indicators, but they are basically looking at the performance of their own company more than the impact of the products on, let's say, externalities that may impact globally. So there is also a need to rethink a little bit how this ESG may be monitored and quantified. However, as we said, we see encouraging and significant progress to address those issues. More and more countries are developing national strategies and setting up international partnerships, including, for example, the European Union, Canada, US with the IRENA. So we see more and more of this integration of the supply of critical materials in their national plans. In the case, for example, of electric vehicles and batteries for electromobility, gigafactories, increasing the pipeline, including a vertical integrated approach, materials innovation to actually replace some of these critical materials by other substitute materials. And in the case of batteries, for example, to reduce the use of nickel or cobalt, now we are seeing more in the market, lithium phosphate, iron phosphate batteries, which 2-3 years ago were not really considered. Now, because of safety issues, are being considered, and because of less dependency on these other materials like cobalt or nickel, despite there is always a trade-off. Despite they might be a bit lower performance in terms of energy density from these batteries, it has other benefits that is already showing an increase in the share of this chemistry for batteries in the market. Sodium batteries has also now been discussed. There are some prospects that this may increase. But again, aspect that we are discussing with our member countries that need to be taken into account is the planning for these new mining areas and facilities. They take a long time, as we have heard from previous speakers before, while, for example, a battery production company facility can take from 1 to 3 years. A mining facility may take between 5 and 15 years. The need for sustainability is important and it's a must. And materials innovation and circular economy, as mentioned by previous speakers, is also critical. The issue is that in some cases, this demand for recycled materials is not there yet. There is still a need for a better understanding. An example is rare earth, for example, where there are already technologies and companies recycling rare earth for permanent magnet, but OEMs are hesitant to use recycled rare earth materials because they have a level of purity that maybe it's not 99%, but 95%, and they have some hesitations to use that, despite they can be used. So there is still more work to be done in that area as well. Now, to try to address this with our 168 member countries, IRENA has established, by request of our member countries, the IRENA Collaborative Framework on Critical Materials. At the moment, we have around 45 countries engaged in this collaborative framework, which is facilitated by the government of the United Kingdom of Great Britain and Peru. And this working group has started its work 1 year ago, and it's focusing its work on 3 main areas. The first one is an observatory to have more transparency and access to data required to have clarity on price signals and demand projections for those critical materials. The second topic we are working on, the countries are working on, is in strategies to de-risk supply. And the third one is around mining and ESG. And in addition to the countries that are working with us, we have a number of partners, including the World Bank, the ITI, the Foundation, the Copper Institute, etc., supporting this work as knowledge partners for these activities. We have also developed, and all the material I have presented today is publicly available in our analytical work. We have all these reports publicly available, 2 on critical materials for the energy transition, 1 deep dive on rare earth elements, 1 deep dive on lithium, 1 on the implications of critical material for the energy transition. There is 1 that is forthcoming, will be published in the first quarter of next year on critical materials for electric vehicle batteries. We will have another 1 working with the World Bank on ESGs for mining, for critical materials for the energy transition. And also next year, we'll be publishing 1 report on the geopolitical implications of critical materials for the energy transition. Unfortunately, I cannot be with you there in person. I regret that, and I cannot see the room, but I trust you have a room full of delegates from countries. So if your country is interested to engage in the collaborative framework or in any of these analytical pieces of work, please feel free to contact me. Email is cfmaterials@irena.org, and we will be very happy to work with you on these topics that we are discussing in this very interesting session. And well, I will remain connected because I understand our panel discussion on answer questions. So thank you very much.
Thank you so much, Francisco. I don't know if you could hear, but there was a round of applause for you. Thank you to all the speakers. This was a really interesting set of talks where we could really understand what the challenges are for different kinds of materials and why we need to do it quickly. So I want to start the Q&A by discussing risks, because there's different interventions that were discussed. For example, from upstream supply to downstream demand, and there is a competition for those, for example, in the hard to decarbonize sectors. Then there is risk in the time for the transitions to happen if we start doing these different considerations apart from price or land use that we need to take into account. And there's also risks in changing critical mineral components in certain applications. So I want to ask all of my speakers to address this risk topic and say what can be done. So maybe I'll start with Jennifer this time to turn the order around.
Thank you for the question. You know, I think the topic of risk, if we look at it there's performance risk, there is the question associated with financial risk, and we have in my mind, there's the durability risk, right? The time for the solution and whether or not this will, the old, and this is, I'm going to date myself, VHS versus Betamax case study example from business school, which you all know, may be very much a US example. But the question of whether or not the market intervention that you're going in with will be durable in the market. So will that be sustained? They require different kinds of management approaches. In terms of performance risk, I think we have a real challenge ahead of us to think about this. If we're going to innovate and reuse, for example, the batteries, one of the things that happened very early on when we were trying to put forward lithium-ion batteries and was the question of how quickly they degraded. You have no durable time horizon for how long the product will perform as you want it. And so the OEMs in particular, when I was working in the private sector, the car manufacturers were unwilling to use a battery swap approach simply because they couldn't guarantee whether or not the performance of that battery that was coming into the vehicle was up to their standard. So what is it that we do to create a collaborative risk management approach to give the consumer and the supplier of that product confidence that if something goes wrong, that will be, we do this all the time with cars in general, right? There's always take-back requirements to fix things if there's a safety recall or something like that. But we haven't extended that into some of these areas. And then the final thing that, let me just say on this question of financial risk, The scale of finance, and this has been the topic at COP all week, right? The scale of finance required to be able to do the transition and the transformation is not coming from government alone. And so where and how government chooses to incentivize private investment to help bolster confidence that that financial risk will be manageable is one of the things that's slowing us down, and one of the things we're going to have to focus on very significantly between business and government if we're going to get this right.
Thank you. Very important. Francisco, I'm going to hand over to you to also address this question of risk. And if you want to focus on the critical mineral side, that works as well.
Yes, thank you so much. Yeah, very important question. Maybe I would cluster this in 3 risks that we consider should be tackled first in terms of critical materials. On the supply side, the accelerating, let's say, the supply of these materials. And this requires, of course, an increase in mining production and refining and processing. What is needed is for investors is to have a clear signal of what will be the demand for these materials, and to have the right strategy, let's say, on, we said it should be vertically integrated, including, let's say, a different approach that is not just mining, it's really the whole value chain. But this issue that new mines, let's say, take between 5 and 25 years is something that needs to be considered, and it's a big risk, of course. So what can we do? On the one hand, is try to diversify locations for mining, diversify also locations for refining, diversify location for processing. And that requires not only the resources, but this requires the skilled people to do it, the industrial capacity to do it, and the right access to ports and trade hubs. Second, very important, more on the demand side, is how to reduce the demand for some of these critical materials, and innovation will continue to be crucial. We need to continue to work on alternative materials for different elements, which is to some extent already happening. For example, in the case of rare earth for permanent magnets, you can have wind turbines, of course, not with direct train generators, but with gearboxes that require much less of permanent magnets, or just induction generators. The thing, of course, is that if you go, for example, offshore, you want a small generators that don't put more risk, let's say, in terms of maintenance of those turbines, but you can manage that in a way. So there is always a trade-off, as mentioned before, on these critical materials. The same with batteries. So you may have less dependency on some materials, but that will have an impact on your energy density or durability or safety. But anyway, I think that are really manageable. It's not really a stopper. And innovation needs to continue to address this from the demand side. And the third one, of course, very important, mentioned before, is the environmental impacts and sustainability. But for the whole value chain, from mining, refining, production, and demand. And we need more transparency also on how these indicators for ESGs, for example, are being developed and accounted by companies, but also the issue around, for example, standards, not only for sustainability, but also, for example, basic things like durability of batteries. Just now, the European Union has issued their durability standard for in-vehicle battery durability, with minimum threshold on how many kilometers these batteries should last. So there is a lot of these still. So we have strategies to mitigate those risks on all these aspects. And what we see is that governments are taking this very seriously, or starting somewhere to take this very seriously. And what we need is to work together to try to learn from each other, to accelerate those good or best practices, and implement this in a globalized market that will not stop, but will facilitate the energy transition.
Thank you. Yes, key points for sure. Peter, Yeah, risks as well, and perhaps if you want to say something about whether that will affect the scenario that you have if, for example, these demand interventions are hard to get by. Or
Thanks very much, Karla. I think the other two panelists have covered a lot there. I would definitely apply a kind of a risk framework to this, and this is something that we are going to go into more detail in our upcoming edition of Energy Technology Perspectives released in January. And really we're looking at the types of things you're talking about in the context of supply chains for each element of the supply chains, through from resource extraction to manufacturing of the components and materials and devices that we need that have been mentioned, electrolyzers, PV, wind, etc. But really looking across the supply chain at risks in a few different dimensions. Several have been mentioned already. I think security, concentration, market concentration, that's been covered. Resilience, to the extent to which, if you have a disruption in one area, is there a way you can make your supply chain more robust with substitutions or reducing the overall demand? In the case of material efficiency strategies, that could be particularly relevant there. I think there's the sustainability dimension, and I would say that this is not something that's unimportant by any means for critical minerals, but we do have to, inform our audience and our policymakers as to the difference in the scale of the challenge with respect to absolute emissions. For the industry sector overall, we're talking about 9 gigatons of CO2 emissions for the industry sector overall. Heavy industries, those main bulk materials that I described in my presentation, are accounting for around 70% of that. Copper is produced in the megatons, but many of the other critical minerals that we're talking about are produced in the kilotons. Steel is produced in the gigatons. Cement is produced in the gigatons. So the scale and the order of magnitude differences between these materials, even if the emissions intensity of some of the smaller volume metals is higher, we really do see quite stark differences in terms of the overall emissions burden. Other bottlenecks, I think one that maybe wasn't mentioned, I might be wrong, is on the jobs and skills side. So the need to retrain and deploy new skills and workers in different sectors of the economy, making sure that just transition elements of the transition are considered properly, that people who are displaced in, say, fossil fuel industries over the transition period to 2030, 2050 are adequately skilled and reskilled and supported in the transition to mining of different materials and different resources. These will be particularly important things to address if we're not to face a bottleneck in some way in that area. And lead times is another thing that has been mentioned that I think is another important bottleneck, particularly on the mining and resource extraction side. But as I say, we're going to cover this all in a bit more detail in ETP in January.
Perfect. So stay tuned because there's so much more to come. Thank you. I think now I want to discuss a bit about the different stakeholders and political will and other kinds of actors that are influencing the decisions that need to be made, again, sooner rather than later. So what kind of pushbacks have you identified and what are ways to go forward? Maybe this time I'll start with Jennifer, maybe again, and then I'll switch it around.
I didn't think I was going to get called on first again. Political pushbacks. Look, we are at a moment where we have to ask ourselves how you break the inertia of our current economic system. And there is a live experiment happening, right now in the United States with the Inflation Reduction Act having just passed, with tremendous levers in terms of financial opportunity for tax credit, for benefits, and for the investment in new technology and partnership between government and industry. The real question I think we all have to grapple with is this one of the time scale. And the ability for us to transform institutions, business or government, has proven to be the biggest challenge that we face. And I don't believe it's the technology. innovation and kind of the can-do attitude associated with making new things happen competes directly with the existing ways that we do things, and those that are investing or are part of a new economy, and the cannibalization, if you're doing that from within your own company, can create real tension. So you see this tug of war happening, and we don't have time for the tug of war. That requires that policymakers recognize, incentivize, and regulate, and put clear indications of where their economies need to be, performance-based indications of where economies need to be. It's not a question anymore of, can we argue about whether or not we're going to phase out coal? It's about economic transformation and all of the elements associated with that. So I think for me, the takeaway is we don't have time for demonstration projects. We don't have time to wait for a gradual shift based on a capital transformation. We have to intervene faster. We have to retire existing assets, and we have to have new business models scale at an unprecedented rate. And that's where that risk piece comes in that we're going to have to navigate. So just a few thoughts.
Thank you. Peter?
Thanks, Karla. I would just focus on one element here. So, I mean, the extent to which the political sphere interacts with the transition, I mean, there are many, many dimensions, but international collaboration would be one. And, if we have a certain political climate, we are likely to have, a better or worse environment for international collaboration. This is between countries, of course, between different regions of the world, when it comes to trade and investment and collaboration on innovation and R&D, collaboration on protocols and standards for producing materials with a certain level of environmental performance. These are all dimensions of international collaboration that will be, to whatever extent hindered or accelerated by the prevailing political climate. We released a report on this topic specifically on international collaboration, and we had as part of the Breakthrough Agenda, it's called the Breakthrough Agenda Report, and actually IRENA were co-authors of that report. And this is an update on, or tracking of international collaboration in the key areas of the breakthroughs, so steel, hydrogen, power, agriculture, etc. I think that this is a key area where I'd say that the two spheres are interacting closely.
Thank you. And Francisco?
Thank you. Yeah, well, I think that, again, a lot has been said again. Maybe from my end, just to highlight that we see that this international collaboration is around these critical materials is taking every time more seriously. And a clear example is our collaborative framework on critical materials. We have 7 collaborative frameworks on different technologies in the agency. And the one on critical materials is one that always has a very big participation of our member countries and one of the greatest interests. So it's clear that countries would like to not only understand what other countries are doing, but also collaborate and exchange some of these practices. We also see these other initiatives like the Mineral Security Partnership that include, I think now, US, Canada, Germany, Japan, South Korea, a number of countries already been established. In the US, this again, ERGI initiative, etc. So we see that this is already happening. Maybe there is still a need, more could be done in more like a dialogue and strategic plans, including the different stakeholders, public, government, but also civil society, private sector, mining companies, to really define strategies that can, to the possible extent, meet the requirements and the needs from all of them to accelerate this transition to the pace that is needed. But there are also some progress in terms of that. And a lot of initiatives. Thanks, Peter, for mentioning the Breakthrough Agenda. Indeed, please go and read it. There are a number of initiatives there for steel, but other like cement and other hydrogen, but already ongoing in international collaboration initiatives documented in that document. So yeah, I think we see progress there, but more to be done.
Yes, thank you. I have some questions from the audience on Slido, so if you have more, please feel free to add them to here. I have some about land management and how, so there's actually two. I'm going to try to summarize them, and maybe Jennifer, this question will be for you. In Germany, wind farms have been removed for increased lignite mining, and what can we do to mobilize global land management, and how can that be done? And similarly, how can we make sure that where the resources are extracted, there is a fair deal for the country where it was extracted from?
It's a very interesting example, the wind farm removal for mining. And I think that there is also a question that we ought to flip around, which is what are we going to do with all the land that is now brownfield land because of mining? And so there's this question of what the dual purposes could be, or the dual uses could be for us to think through. I really want to turn, though, to this sort of the questions associated with equity, justice, and resource extraction and land. The WRI for decades has been working on land tenure rights as part of a really important part of our governance systems work. The land tenure challenges that we're facing are only one of a number of different questions that are going to be facing governments and local communities. And part of the challenge has been this question of who has the legal authority to make decisions. But even when you have clarity around legal authorities, you also then have this question of where and how the community benefit is articulated, and the level of engagement and participation by local communities in the mining sector has a very unfortunate history. In order to change those that equation, there are many folks out there working on the Extractive Industry Transition Initiative is one of those that I think is certainly allows governments to have a mechanism by which to evaluate and look at the kinds of practices and work with business. The question then of who benefits and in what way. Is it enough to have a school on site? Is it enough to have a local job? Is it enough to recognize the level of destruction that may occur, water pollution? The considerations around equity are things that have not been grappled with very effectively by institutions, but government or private institutions, and will require, I think, the just energy transition conversation will require academics, practitioners, and governments to formulate a very significant shift in the way we evaluate project opportunities.
Thank you, definitely. We have just 5 minutes left, so I will summarize a bit two questions that Jakob was making about whether there can be scenarios limiting household vehicle use and strengthening public transport and just connecting more supply and demand side. So maybe Francisco, if you want to comment on this briefly, and then I can have some more time for an extra question. Francisco?
Yes, sorry, I couldn't hear very well, but can you hear me?
Oh, sorry, yes.
Connection was not so...
So this question was about...
I think it was about modal shift to use more public transport instead of private. Was that the question?
Yes.
Yeah, okay, great. So yeah, the short answer is yes. Our World Energy Transitions Outlook model includes a modal shift as part of the model. And but the modal shift includes many things, from not only private cars to public transport trains, but also in some cases
Oh, sorry. I think we lost him. So that means, yes. Peter, do you want to come in?
I can come in on that. Yeah, in the scenarios that we put forward that I've talked about today from the International Energy Agency, behavioral change is the kind of broader category of strategies and measures that can be taken at various points in the supply chain through to the end user. Many important things happening there, whether it's more sustainable reduction in waste, through to modal shift, whether it's through to... Oh, thank you very much, Jim. I'm not much luck with this one now. Sorry, I'm probably causing havoc for the audio folks at the back. So I mean, on the behavioural change side, with respect to end user behaviour, whether it's dietary changes and reductions in food waste, these are things that are considered in our scenario, especially with respect to the extent that they reduce land use change emissions and emissions beyond the energy sector. But then within the energy sector, as I think Francisco is beginning to highlight, modal shifts in the transport sector, reductions in the overall amount of business class travel and so on, things like that on the aviation sector. And then in the industry sector, things to do with the behavioural aspects of the material efficiency strategies that need to be enacted across the behavioural change. Different design practices, different ways in which we use materials at the end use stage in the value chain, extending the life of different assets and different end use products. These are all things that require some degree of behavioural change. So those would be the main considerations, I think.
Thank you. And for the last question, I just want to say or ask the speakers to do two things. Quickly reply, would you say what would you respond to anyone who thinks that material security is an issue that puts too much at risk in the transition? And the second thing I want you to say is just a final sentence with what is the key takeaway from this? So, Peter, I think you're going to go first again.
I think with the response to someone who says whether materials are important or not in the transition, well, I think we've all collectively shown today that they're very important, and that there are incredibly important aspects to consider in both the bulk materials and critical mineral side of the equation, and with respect to the other dimensions of sustainability associated with producing those in the future. And one key takeaway for me would be this. I would hark back to the innovation point. So on the bulk materials side, I would one thing to take away would be we need to bring the technologies that can achieve substantial reductions in emissions intensity through to commercial deployment, if I was to just have one. But I think there are many important points that you've all raised.
Yes. Jennifer?
Let's see if this one, okay. So the answer would be yes, it's critical, absolutely critical that we improve circularity and build a regenerative economy. The second question, what would I say?
Key takeaway.
Key takeaway. For me, the key takeaway here is that we have to create a consumer that cares, and that the issues are not going to ultimately be determined by the supply constraints, because we are very innovative as a species. The challenges are ultimately going to be about whether or not we can create the products that people will accept in the time horizon that we need them, and with the right information available by policy and by consumers to demand that.
Thank you. Francisco, I don't know if we got him back. No, I don't think we did. Sorry. Well, thank you so much. I hope this was an informative session, and that we brought out some topics that sound really interesting and make you want to go and find out more. There's many more publications that authors here have done, so please go look them up or look us up on social media, and I'm sure we'll be happy to respond to anything. Thank you so much for the organizers as well.
you.